Hello students, I hope you are making full use of these videos. Apart from these videos, you must also go through your school textbooks so that you are able to synchronize it better and have a better clarity on the subject. So now the next case remaining is basically spheres, spherical shells, hollow and solid, and again we are going to make use of Gauss law. Already I told you what is Gauss law. Flux phi is equals to integral E dot ds, and that can be also written as q in by epsilon. Q in is the enclosed charge inside that imaginary Gaussian surface. Imaginary Gaussian surface should always be a 3D Gaussian surface and it has to be a closed surface. So that is what is this. Here is the symbol of integral, and when I am putting here closed, it means I am taking the closed surface integral. So that is the concept of Gauss law. So now let us talk about spheres. So basically spheres we can divide into two segments. One is hollow spheres and another is solid spheres. Hollow sphere will be something like this, and solid sphere means it is filled from inside also, means it is filled entirely with matter. So that is your solid sphere. In hollow also then there are two cases. One is conducting. Conducting means metallic, and another is non-conducting. Non-conducting, that is basically your insulator or insulating body. There can be two types of hollow spheres. One is the metallic body, which is hollow from inside, and another is maybe a non-metallic body, which is an insulating body, like it may be a wooden body or something like that, but inside it is empty. I mean there is nothing inside, that's why we are calling it as hollow. Same in solids also there can be two cases. One is conducting, metallic conducting, and another can be non-conducting, and non-conducting body is also known as insulating. There is one more word of insulating body, non-conducting, which is your dielectric. Some textbooks this word use this word also, dielectric. So basically if you see carefully, there are two types of spheres, hollow spheres and solid spheres. We need to calculate the electric field due to these spheres at some particular points. But first, if we have a clarity of spheres, then our understanding of electric field will be better. So there are two types of spheres, hollow and solid. In hollow also again two types are there. Conducting metallic bodies or non-conducting, another name is insulating, also known as dielectric. Same way in solid spheres also there are two types, conducting and non-conducting. In conducting again there is a metallic body, and in non-conducting again there is a insulating body or dielectric body. So that is your cases of spheres. Now let us go one by one. Now here I want to make one thing clear, that the results for hollow conducting, hollow non-conducting and solid conducting are same. The results for hollow conducting, hollow non-conducting and solid conducting, the results are same. So hollow conducting, this is hollow conducting, hollow non-conducting and solid conducting, the results are same. And one more case we will take separately for solid non-conducting. Solid non-conducting, non-conducting body or a insulating body. So the results are same for hollow conducting, hollow non-conducting and solid conducting. So first let me do one thing. Let me divide this entire thing into two parts, hollow conducting, hollow non-conducting, solid conducting. That I am going to discuss first, electric field due to these type of spheres, and then we will go for the solid non-conducting. This is also known as shell. The another name of this is shell, spherical shell. So I hope this theory about spheres is clear to you. So you can note it down so that I can move on the derivations of electric field due to case 1 and then accordingly case 2. You can so first we are going to take case 1, which is hollow conducting, hollow non-conducting or solid conducting. These type of spheres we are taking. Point number 1 that should be clear to you is that whenever we give a charge to a sphere, this type of sphere, whether it is a hollow conducting body a hollow non-conducting body, or a solid means something is filled inside, conducting body. Conducting means metallic body is a good conductor of electricity, and is a metallic body basically. So whenever you give charge to these three type of bodies, then charge will not accumulate inside the body, but it will automatically appear on the surface of the body. Hollow conducting body is there. If we give charge to it, inside nothing is there, so where would the charge will appear? Obviously when we give charge, you assume charge is you know that it's an intrinsic property like mass. So when you give charge to the body, but inside nothing is there, where the charge will stay, so automatically the charge appears on the surface of the body. In solid conducting also, in hollow, so obviously it has to appear on the surface only, so there is no doubt here. In hollow conducting, hollow non-conducting, the charge has to appear on the surface only, but in solid conducting also the charge appears on the surface. So whenever we inject any charge to these type of spheres, the charge will automatically appear on the surface. So point number 1 is very much important, that charge given to above spheres, charge given to above spheres gets or appears on the surface, on the top surface of the body. So this point is very much clear to us. So let us take case number 1. Case 1. Case 1 is that, let us say this is your spherical body. Spherical body is there. It may be a hollow conducting, hollow non-conducting, or solid conducting. Whenever we give any charge to this body, then where the charge will appear? Suppose if we have given a charge Q to this body, then that charge Q will appear on the surface of this body. Let us say this charge is plus Q. So the plus Q charge is appeared where? On the surface of the body. So this is what the overall charge has appeared like this. Now we need to calculate electric field. So electric field, how can we calculate? But first we need to know where to calculate the electric field. So there are 3 cases. One is at a point P outside the spherical shell, we are calculating the electric field. In next case, we will calculate the electric field on this sphere, and in case number 3, we will calculate the electric field inside the sphere. So now this is case number 1, that is electric field. Let us say the radius of this sphere is r. Radius of the sphere is r. So we are calculating electric field at a point P. At a point P outside the sphere. At a point P outside. So let us say that this distance is r, small r. This distance is small r. So can I say that r is greater than r? Obviously I can say r is greater than r. Where am I calculating the electric field? What are we doing in this particular section? We are calculating the electric field due to spheres. We have calculated electric field due to a point charge. Formula was kq by r square. Due to a ring, formula was kqx by r square plus x square to the power 3 by 2. We have also calculated electric field due to a thin infinite long wire. Formula was lambda by 2 pi epsilon naught r. We have calculated due to thin sheet, sigma by 2 epsilon naught, due to thick sheet, sigma by epsilon naught, and now we are calculating electric field due to a charged spherical surface or charged spherical body. In case 1, we have taken hollow conducting, hollow non-conducting, or solid conducting. So we have given a charge Q. As I told you, the charge given to this type of spheres always appears on the top surface of the spherical shell or spherical body. And we are calculating electric field at a point P which is outside the sphere. Outside the sphere. So we need to make use of Gauss law. So let us apply Gauss law. So what does Gauss law say? The first important step in Gauss law is to choose a proper Gaussian surface. So what is the Gaussian surface here? Tell me what type of Gaussian surface you are going to take. I told you that there are 3 types of Gaussian surfaces you can take: spherical, cubical, or cylindrical. In our earlier 2 cases where it was a line charge or a plane sheet, we have taken a cylindrical Gaussian surface. Here I am going to take what? Here I am going to take a spherical Gaussian surface. A spherical Gaussian surface. Spherical Gaussian surface. Now the next point would be, after choosing the spherical Gaussian surface, I am drawing the imaginary 3D surface. So this is our spherical Gaussian surface. This is our spherical Gaussian surface. Let us see how to calculate here. So in this spherical Gaussian surface, what we are going to do here is we are going to apply Gauss law. So what is Gauss law? Net electric flux phi is equals to integral E dot ds, which is equals to Q enclosed by epsilon naught. Yes or no? This is a Gauss law. So net flux phi is equals to E dot ds. Now tell me, at this point, let us say here you are taking a small surface ds. At this point, due to this sphere, where will be the electric field? Obviously, because of these positive charges, electric field will be in this direction. Suppose here we are taking a small element ds, a small surface ds, then here where will be the direction of electric field? Because of this positive charge, it will be away. You know, because of a positive charge, electric field is always away. And the area vector is also in the same direction. Here also area vector is here. I told you, area vector for a 3D surface, normal vector perpendicular to the surface. Here suppose you are taking electric field is in this direction, area vector is in this direction. So electric field and area vector are in the same direction. Electric field is a constant quantity, so electric field will come out into E dot ds. Since E and ds are in the same direction, angle between them is how much? 0. So E ds cos 0 means 1, yani E into ds. So E will come out, integral ds. ds means ds plus ds plus ds plus ds. How many times? Infinite times. It means the total surface area of this Gaussian surface. What is the surface area for a sphere? 4 pi r square. What is the formula? 4 pi r square. So can I say like this, 4 pi, what is this distance? R. Obviously for the Gaussian surface, radius is r. So my formula becomes E into 4 pi r square is equals to Q in. What is the charge enclosed in this Gaussian surface? In this Gaussian surface, the charge enclosed is this capital Q only. Yes or no? In this Gaussian surface, what is the total charge? Total charge is the sum of all the small charges, which is basically your capital Q. So capital Q by epsilon naught. So from here what can I write? I can say E is equals to Q by 4 pi epsilon naught r square. But what is 1 by 4 pi epsilon naught? 1 by 4 pi epsilon naught is k q by r square. So it means that this formula, have you ever seen this formula earlier? Yes, you might have seen this formula in case of point charge. In case of point charge also the formula was same, kq by r square. It means here also for a point outside the sphere, if the point is outside the sphere, the electric field at that point is kq by r square radially outward. Suppose the point P is here, then electric field is in this direction. If the point P is here, electric field is in direction. So electric field is kq by r square, I may say radially outwards. So this formula is similar to that of a point charge. So I can say that the entire sphere for the outside point is behaving like a point charge. The sphere for the outside point is behaving like a point charge, and that is what the formula also says, kq by r square. Next we need to go to case number 2, when instead of calculating at an outside point, we will calculate at the point on the sphere and then we will move to inside point. So let us do one thing, you note it down so that we can move to case number 2. Remember what is here the formula for outside? Kq by r square, whether it is hollow conducting, hollow non-conducting or solid conducting. For all the 3 cases formula is same, kq by r square. So note it so that I can move to the next case. Okay, so let us continue to case number 2. Case number 2. In case number 2, so this is our sphere. This is our sphere. I told that in these type of spheres, charge will always appear. Charge will always appear where? Charge appears on the top surface of the sphere. Top surface. So if we give a charge q to this, it will appear on the top surface of the sphere. When we give a charge q, it will appear on the top surface of the sphere. So again let us say here also radius is r. here also radius is r. You remember for the earlier case, when r was greater than r, what was the electric field? kq by r square. When r was greater than r, electric field was kq by r square. So that was case number 1. Now case number 2, we are taking r equals to r. It means we need to find, we are finding electric field E at a point P, on the surface of sphere. On the surface of sphere, we are finding electrical field at a point P on the surface of sphere. At this surface we are finding the electric field. So basically what we can do here is that in this formula, can I substitute r equals to r? Yes. Or you can take an imaginary Gaussian surface like this, which is just greater than r equals to r. That way also you can do. Or you can directly substitute in this formula, E is equals to kq by, let us say this is that point, so E at P is equals to kq. When r becomes equals to r, it becomes kq by capital R the square. So that's the formula, kq by r square. Or you can also apply Gaussian law. So Gauss law says that phi is equals to integral E dot ds is equals to q in by epsilon naught. So this time becomes E into integral ds will become what? 4 pi capital R square, and q in is nothing but q by epsilon naught. So when this will go in the denominator, you will get the same expression. Electrical field at the point P, which is on the surface of the sphere, is kq by r square. So if it is r is greater than r, it means for the outside point, kq by small r square. For the point on where the radius is r, kq by capital R the square. That's the formula for your point on the sphere. Now let us take a point inside the sphere in case number 3. I hope case 2 is very much clear to you. You can note it down. You have to remember these formulas, because directly in your exams these formulas are asked, both in board exams as well as in your competitive exams. We will take up more problems also, but first try to understand how to apply Gauss law. I hope everyone is clear about how to apply the Gauss law. With that we will move to case number 3. Okay, so let us see case number 3. Now case number 3 would be, this is a sphere of radius r, and we need to find the electrical field at a point P inside. Now when we give a charge q to this sphere, the charge q gets distributed on the entire surface of the sphere. And we need to find what? We need to find the electrical field at a point P inside. So let us say that this distance is r. So this time we are finding E at a point P inside the sphere. So that makes our case like this: r is less than r. In the first case r was greater than r. In the second case r is equals to r. In case number 3, r is less than r. So let me do one thing. Let me draw a imaginary Gaussian surface. So first I am taking a imaginary Gaussian surface. Obviously that surface would be a spherical surface. This is that spherical surface of radius r. I have taken an imaginary Gaussian surface which is a spherical surface. This is that surface of radius r. So what to do here? Let us apply Gauss law. So Gauss law says that net flux phi is equals to, what do you mean by flux? The number of lines, field lines crossing an area perpendicularly. Flux is equals to integral E dot ds, which is equals to q in by epsilon naught. Now tell me one thing. In this Gaussian surface, inside this Gaussian surface, what is the charge? What is q in? Q in. Obviously q in is what? 0. Q in is 0 here, because there is no charge contained inside this spherical Gaussian surface. Why? Because the charge entirely, whatever we have given, whatever charge you have injected to this sphere, the entire charge got distributed and appearing on the surface. So there is no charge inside this Gaussian surface. It means the q in is how much? 0. So right side quantity becomes what? 0. it means ds cannot be 0, so E obviously has to be 0, because E dot ds became 0 because q in is 0, so electrical field E became how much? 0. So electric field at an point inside this hollow conducting, hollow non-conducting or solid conducting is 0. Inside a conductor there is no electric field, because charge does not reside inside a conductor. Since the charge is accumulated only on the surface, and when we have to find the electric field at a point inside, when we are taking the Gaussian surface inside that Gaussian surface no charge is there, because the entire charge is distributed on the surface. So because of Gauss law we can say that electric field is 0, and that is why I was saying that charge appears on the top surface, because there is no electric field inside the conductor, inside the sphere, and hence no electric field was there, so there was no charge enclosed, and hence the entire charge has been appearing on the top surface. So from here we get a very important point, that charge does not reside in the conductor. In the conductor means inside the conductor, it appears on the top surface, and electric field inside is how much? 0. So that's, I think, the case for your inside point is also clear. So let me do one thing, let me make a small summary of this, and I'll draw all the graphs for outside point, inside point, and on the point, on the surface, and I'll draw the graph, and you can draw the entire conclusion from there. Meanwhile you can, so I think all the three cases are clear to you for a point inside. So let me do like this: inside R is less than R, on R is equals to R, and outside electric field outside R is greater than R. For inside, what is the electric field? 0. On, what is the electric field? KQ by capital R the square, and outside electric field is KQ by small r the square. I can draw a graph between electric field E and radius R. Let us say here R is equals to R. So till R is equals to R, electric field is how much? 0. Suddenly at R is equals to R, electric field becomes KQ by R square. This value is KQ by capital R the square, and after R greater than R, again because see here capital R is a constant value which is radius of that sphere, so that's why a constant value I am writing, KQ by R square at R equals to R, and suddenly after R greater than R, KQ by small r the square. Now small r is a variable quantity, as you will keep on moving away from the surface or from the center of the sphere, R value will keep on increasing. So R keeps on increasing, E keeps on decreasing. So the graph becomes like this, is a kind of basically you are inversely proportional to 1 by R square. So this is the graph basically for your hollow conducting, hollow non-conducting, solid conducting spheres. So that is about the theory of spheres, and we are left with one more case, which is solid non-conducting. Solid non-conducting means solid insulating body, and in insulating body charge will reside inside the surface also. Here charge is not residing inside the surface. In solid non-conducting, solid insulating, charge will reside inside the surface of the body. So let us see how to tackle that type of problems. Meanwhile you note it down, and I'll take up that particular case in my next video with more problems coming from spheres. That will be the last video as far as electric field is concerned, and then we will move to potential. That's it for this video. Thank you.